got it close anyway. He had his master's degree in oceanography from Dalhousie in 1998. Graduated with a PhD in 2002, also from Dalhousie, and then took a position at the University of North Dakota. And he has very recently come down to USM, I guess in the last 6 months.
No, just last month.
Just last month, okay. Where he has an endowed chair over in marine sciences. So we're pleased to have him, and he's going to talk to us about light scattering and particles in the ocean.
Thank you, Eric. And this is the work, and I did about the last 10 years, one of the major work I did. So today, and I'm happy here to share what we have been able to achieve in light scattering. And the title is The Black Man and the Elephant to Light Scattering and Particle in the Ocean. You will get an idea of what that means. So basically it's a light scattering. So first let's see what is the scattering of the light. Let's see if we have the light coming in, right? Light coming in, and it hit a particle. And the energy of light scattered in all the directions. So let's measure the light at one direction. How much light scattered by this one particle in that particular direction? And if we measure the light is this, and we measure, this is the energy, let's say it's the J. And divided by the instant light is typically assumed to the parallel light, so it has the energy per square meter, so this is the parallel light. So if we divide this, we get this called the differential scattering cross-section. Why it's called the cross-section? Is because it has a unit per square meter area. So if we do this, we get this scattering cross-section. So now this is one particle, and we don't deal with one particle, right? We work in the ocean, and we have many, many particles. So this is what we do. Let's say we have many particles, and we do the same experiment. We shoot the light, and this is all the particles. Let's say we have a sample, and we do the same thing. We measure the light all coming from an angle. Now we do this, we measure the energy divided by instant energy. Now because we are looking at this volume of particles, we divide by volume. So this is how much volume. Now we do this, we got the volume scattering function, and it's beta. And it has a unit per meter and per solid angle. And what is the solid angle? If you imagine solid angle is the light coming in one direction, from the source and spread out like ice cream cone. So that is to define how big that angle is. So this is the solid angle. So now we have this volume scattering function. If we see here we have one particle, if we assume within this volume all the particles are the same, we have n number of particles, and this volume scattering function is simply n multiplied this single particle scattering cross section. So now this is simple way. This is exactly the way we quantify the scatter light at different angle. Now, we have this scatter light at different angle, but typically when we study the light, we want to know what is the total amount of light, regardless of different angle scattering, and we just see what's the total amount of light that being scattered. So what we do, we take this, we basically add every single angle. This is in this angle, this is in this angle. We add everything together, and we find what is the total scatter light. And we call this scattering coefficient. And when doing this, we typically assume this, what we call azimuthal symmetry. Azimuthal symmetry, what that means is this. Like if light coming from back of me, I'm a particle, so this is one direction scattered, and I'm seeing all this direction where you see it forming the same angle with this forward, all around this thing, all the same. And this is typically true when we deal with natural particles where they are randomly orientated. So if we assume this, when we sum everything, now this we can mathematically describe how we calculate this total scattering coefficient. And we study ocean, and very often we use satellite. For satellite, what the case is, sunlight coming in and reflected backward, right, recorded by the sensor. In that case, most light received by a sensor is backscattered. Sunlight coming in, backscattered to the sensor. So for the remote sensing, or we call the ocean color, often we are interested in this parameter called the backscattering. Backscattering coefficient is the same, definition is the same, except we only look at the angle in the backward angle, which is from 90 degree to 180 degree. So that's the backscattering coefficient. Now, if we normalize this volume scattering function by the total scattering coefficient, we got this symbol didn't show up. Basically, it's the bar over the beta. It's called the phase function. Phase function, by normalization, we just look at the shape. We ignore the magnitude, right? Now I see we measure the scatter light angle, a scatter light at a particular angle. What happens if you measure the light at the zero angle? Basically what that means, we just look at the light coming in, we look at the exact direction where light coming in. All we see, we measure the light at the zero scattering angle. This is called the transmitted light. We can measure the light here, and we can do the same thing as we did before, which is measure the transmitted light, divided by incident light, and divided by volume. And this we got attenuation coefficient, C. Now we can do another exercise, basically, we measure how much light absorbs. What is absorbed is light coming to a medium, either scattered or absorbed. Absorbed is absorbed by the medium, turn into heat, or do some others like photosynthesis. So if we can measure this absorbed light and we do the same operation, we got absorption coefficient. This is how much light is being absorbed. And by energy conservation, we have this C, mean total attenuated light is either absorbed or scattered. So C equal A plus B. And I don't know if any of you have ever made such a measurement, if you heard the AC meter like that, this measure either A, absorption, or attenuation, that is C. So now we have the optical properties. We have the absorption, we have scattering, we have attenuation, and we have the volume scattering function. All those are the function of wavelengths. I mean, what is the color of the light? If we look at the blue color, green color, red color, infrared, they're all different. The optical part all vary with the wavelength spectrally. However, but only one, this volume scattering function beta, or we normalize with the phase function. Only this property vary with the angle where you look at this. Okay, only one. Only this one vary with the angle of observation. So this additional angular dependence contains rich information particles. Now the idea is, if we can look at this, probably we can study more what is the particles. So what kind of information this angular distribution of scatter light content? Number one, it contains information about the size of particle. Smaller particle, smaller size, or particle bigger size, they scatter light differently. And in this case, I just simply simulate particle of different size. And if you see this black line, relative smaller particle, and this little bit darker line, the relative slightly bigger particle, and this is the lighter line, even bigger particle. If you look at this, so X is angle, Y is how much they scatter. So you see this, they're different. So if particle size is different, the way the angle scattered are different. What else? The other is it also varies with the composition of particles. What the composition we see particle, organic matter, inorganic matter, all different particles, like we have bubbles and we have other things. So it also varies with what type of particles they are. And here what the type we typically use refractive index. It's an optical parameter associated with the composition particle. And here we see, if you see this is all the black line we calculate for bubbles, air pocket in the water, bubbles. And those are the gray lines are all for any other particle. If you look at it, yeah, there are many parts that are the same, but if you look at this scattering angle at 80 degree, it's totally different. So if you imagine, if you measure the scatter light, just look at the 80 degree, we can separate the bubble from any other particles. What else? And here we can look at this. There's no bubble, they are all particles. And the particle has a different refractive index. And you can see for the different reflect in this angular distribution, they are different. So this angular distribution also depends on the composition of particles. It also depends on the shape of particles, like a spherical particle or different shape. They will be this angular distribution will be different. Here you see all the colored line is a calculate for particle with this shape, very weird six-sided hexahedral shape. And this black line is we calculate just for spherical particle, just a sphere versus this. If you look at this sphere, this black line versus this blue line here, and they all have the same refractive index, only difference are the shape. You can tell they are quite different. So this angular distribution also varies with the shape. The last one is also varies the structure. What is the structure of particle? That is, some particles they have different components, like phytoplankton, right? Inside, at least they have a plasma and they have a chloroplast. So that's structure. So here we simulate, this is simulate, and this is the bubbles. And this is the bubbles coated with organic film. There are always bubbles in the ocean, but most bubbles, their surface is coated by organic film. And we simulate this, if you look at this, they're in this part of the angle, they are very similar, but in this part of the angle, they are very different. And this is the simulation, this is what we did in the lab to see how this clean bubble versus coated bubble behave differently. So they are very similar. So now this angular distribution also varies with the structure of particles. Now imagine we see, this angular distribution scatter light tells a lot of things about particles. It tells the size, it tells the composition, tells about the shape, tells about structure. So now if you imagine, if you just look at the scatter light at one angle, right? At one angle we look at different. Then if that's the case, we don't know, if at one angle, a few angles, they're different, but we don't know that the difference is because of size, it's because of composition, or it's because of the shape or structure. So we don't know what caused that change. This is just looks exactly like a blind man touch an elephant, right? We look at one angle, let's say this blind man touched the tail, they feel, it's a rope. It is a rope if you just touch the tail, right? There's nothing wrong with it. This blind man tells absolutely true, it is a rope. However, if this blind man touches his tusk, it's like a spear. It is like a spear. This is look like, if you just look at the scattering at one angle, two angles, so we really don't know exactly what causes light to change. On the other hand, if we observe the scatter light at many angles, or in another way to see, if you have the sixth blind man and touch the elephant, now we can probably come through a complete picture of elephant. If it had this kind of tail, this kind of body, this kind of legs, or this kind of ear. You put them all together, yeah, this is an elephant. So this is the idea. If we look at the scatter light at many, many, many angles, then we can reconstruct, oh, what the particles are that scatter light. So the concept is very simple. The concept is very simple. If you look at this scatter light, and it is possible to figure out what the type of particles that scatter light. So what are the challenges? Why people don't do this? The challenges are, number one, we have to measure this scatter light, right? We have to measure at many, many angles. This number is accurate. We have to measure it. The second challenge is we have to know better about the seawater. We study ocean, particles exist in the ocean, and particles scatter light, water also scatter light. If we want to know the scatter light that's caused by particle, the first thing we have to remove the scatter light that's caused by seawater. So we have to know the seawater very well. And in many cases, actually in vast majority of the ocean, where the clear oceanic water, the scattering by water is much greater than scattering by particles. So it's important to remove this part of the scattering if you want to study particles. And the last challenge is, if we have this many, many angle measurement, and we have to be able to construct the picture. In other words, we have to have that appearance that after listening to the story by 6 blind men, they say, oh, this is the elephant. So we have to have the model or algorithm or method to infer the information about the particles from the angular measurement of the scattering. So those are the 3 challenges. And over the past 10 years, we have tried to overcome each of those challenges, try to move forward in this field of the study. So number one is the measurement. And this figure summarizes the historical measurement mainly conducted in 1960 and early 1980s, only a few observations. Now, they are quite challenging to observe this, particularly in the field, this light scattering by the particles. And this instrument is made by the Pedal, and he was from the Scripps Institution of Oceanography. And so he measured this orange line at his measurement. Over this time, there are many other measurements, but you can see only his measurement cover a much wider angle range. Because of this, there are only a few measurements, and over the past, or at least before 2000, or in the 20th century, and most people study those particles, and they only use Pedal's measurement, assume this is a representative of the particles in the ocean everywhere. And Pedal measured this in 3 locations in calm the ocean, Bahama Island, and Southern California offshore and San Diego Harbor. And that 3 locations, many people pick 1 location, or some people average those or use it as a representative of the particle. Such apparently this is not good enough. The technology advancement after 1990 really renewed or rekindled the interest in this field measurement of volume scattering function. And those are a few instruments. I don't know if you know this, the hydroscatter by Hobby Lab. Hobby Lab no longer exists, but they did produce a very good instrument called Hydroscatter 6. When I was a PhD student at Halsey, we had one of this, which measured the scatter light only at one angle, 140 degrees at 6 wavelengths. And this is an instrument made by a wet lab called Eco Backscatter, probably many of you heard. And there are many versions of this Eco sensor, and typically it measures the volume scattering at one angle, different angle, 124, 142, or 150 degrees, sometimes at one wavelength, sometimes at a different wavelength. So those commercial instruments measure the scattering only at one angle. And there are commercial instruments measure scattering at multiple angles, like this is at least 100, and many people I know, many people at least in the marine science, has this instrument. This instrument measures the scattering at near forward angle. What near forward angle? From about 0 to 15 degree and 32 different angles between this range, angular range. This is what the instrument looks like, list 100. And this is another one, list of VSF. And I have one of this. This is measure. This is in the forward is the same as this. Measure the scattering at 32 angles, and also measure the scattering from 15 to 150 at 140 angles, which measured by this little window. So those are the commercial instruments, and this one only appeared very recently. In addition to those commercial instruments, there are some prototype, and we just one in the world that built to measure this volume scattering function. And this one called the volume scattering meter only operates at one wavelength, but it measures the scattering at over 600 angles from 0.6 degree all the way to 177 degree, and every increment 0.3 degree. This instrument I work when I doing my PhD degree study. And there's upgrade of this version is measured at 8 wavelengths, and this one was developed, not developed, NRL have this instrument developed, and now it's owned by Alan and Derek in NRL. So this is how this instrument looks like. This is a very smart design. It's designed by Ukrainian Academy of Science, a group of scientists they designed. This is light source, and this is the detector, and this is this core. The major part of this instrument is this prism. This is like a periscope, the submarine periscope prism. This prism rotates and looking at the different different angles. Looking at the scattering of the different angles, this rotates, and the light source and the detector are all fixed. And this is what this instrument looks like. And I work with the instrument a lot. I still work with the instrument. And this is another one prototype called the Mascot. Mascot was initially developed by Wet Lab, and it never commercialized. There's only one here, and it's Podolsky, and they have this. And this instrument compared to this, it only measures volumes at the 17 angle. But the good thing is that very high frequency. It has an acquisition frequency at the 20 hertz. It's really fast. You can acquire data at very high frequency. Excuse me. All of the instruments I have worked with, and still work with those instruments. So now we have all those instruments, and we made measurement, and we made a lot of measurement. But as you know, when you operate the instrument before any operation, you have to know how instrument works, right? And sometimes we call the calibration. This instrument, we use this, this is this MVSM, this is the list 100. We use these two combined, we measure. And now in the lab, we validate if the measurements are good. How we do this, we put standard spheres. And standard spheres, we know the spherical particle, we know exact size. If we know their size, we can calculate what the angular distribution of the scattering. So here is the red line is what we know we calculate given the size of the bead, and to the blue line what actually we measure. You can see this measurement and the simulation agree very well. This is one test, we use 2 micron bead. This is another one, we use 20 micron bead. So now we know this instrument works very well, at least agree with the theory. The next one we do, because we have many instruments, right? We all measure light scattering. The one we do, how about we do an inter-instrument comparison? Inter-instrument comparison. And we have AC9, and BC9 we measure attenuation, measure absorption, then by subtraction we can get total scattering coefficient, and also we can use this volume scattering function, total scattering coefficient, and this x-axis was the coefficient, scattering coefficient obtained by AC meter, and this obtained by volume scattering meter. Then you can see the agreement is very nice at all those angles, all those wavelengths to the wavelength. And here we did another comparison. We compared the hydroscope. Hydroscope measure the scattering at 140 degrees, so we compared it again, agreement very well. What we found out is the different instrument we compared the agreement within 10%. So we know the instrument works, although the instrument works. With the confidence of the instrument, and we went out to the measurement, and over the past 10 years, we measure in many places. We measure in Chesapeake Bay, Mobile Bay, Monterey Bay, Leo 15 sign here, and we also in the open ocean. This is the Gulf of Mexico, and Gulf of Mexico and the North Atlantic Ocean, and in the Pacific Ocean. And those are just some data we measure at a different location. So now we meet the first challenge. We acquire data, right? We acquire data. It's the measurement. So the next challenge we see, we don't know how much, we have very, very limited knowledge exactly how much seawater scatter light. So we need to study that. Seawater scattering is a fundamental property. Many prominent scientists had studied this, like Einstein, Raman, they all studied this, exactly how much water scatter light. But there are very little measurement. The theory about the scattering of a pure water, and if we look at the light scattering theory, for anything pure, it should not scatter light. Okay, anything pure should not scatter light. So people have been puzzled why this pure water can scatter light. The theory which is put forth by Einstein and Smoluchowski is this. The theory of this water scattering is this. Imagine this is a little volume, very tiny volume. And within this volume, because we know molecules are moving, thermal motion, right? Molecules are moving, constant moving. And in this case, what is you see, at this instant, there are 3 water molecules. There are many molecules here in this little volume. And these 3 water molecules move into this volume. Because it's moving into volume, it causes a little in the small scale change of density. Because the volume doesn't change and suddenly 3 molecules come in, there's a local change of density. If there's a local change of density which I use delta rho, it's called refracting index change. If refracting index change, it's scatter light. So this is the theory, fundamental theory, why something like pure water or pure liquid scatter light. This is the macroscopic fluctuation in refracting index. This is the theory put forth by Einstein and Smoluchowski, and if you see, this is pretty much a density fluctuation caused by refracting index fluctuation, so this term. And so this is the developed theory for pure water. But what happened to seawater? The difference between seawater and pure water, we all know they're salt, right? They're salt. So the first part is still the same, and there's this macroscopic fluctuation of density. The only difference here, the fluctuation could be caused by a water molecule or salt ion. So here, there's a thermal motion of those called fluctuation of density. And this is exactly the same, principle is the same. In addition to this, there's some other changes. The other change is this. If density doesn't change, however, salinity change. You imagine this. This is same volume. At one instant time, I have 2 ions moving, and at the same time, I have 4 water molecules move out. Let's just assume those 2 ions had the equal mass of these 4 water molecules. So they goes in, ion goes in, water molecule goes out. The mass doesn't change because we assume they have the equal mass. So the density doesn't change. However, what's changed is salinity. That we have ion come in, we have water molecule go out. So we have concentration change. This concentration change also called refracting index change. So this is for the seawater light scattering. In addition to this density fluctuation, there's also additional fluctuation caused by concentration. This part, this concentration fluctuation had never been studied, and we are the first. We developed this analytical formula to describe this concentration fluctuation. So this is one of the work we did in 2009. And also we improved the Einstein's small Chomsky equation. We used better approximation than before. Because of this, now we can simulate water scattering much better than used to be able to achieve. Andre Morel and late Andre Morel, and he measured this scattering for pure water and for the seawater at one salinity, 38.4 at one salinity. The blue dot, his measurement. This figure is for pure water, this figure is for seawater at 38.4 salinity. The blue dot, his measurement. The green line are the theory, the previous theory. You can see the green line doesn't agree with the blue dot. In general, the trend are similar, but the value are different. Here, the x-axis are wavelengths. And the red line is our model. So with our model, we can reproduce this measurement very well. So that means our model works. So this figure is simply shows exactly how this seawater scattering changes with salinity, and our prediction is nonlinear. So as the salinity goes high, it goes this way. That before people have been assumed it's linearly increase, because they don't know. People before we don't know, simply assume the linearly increase, but in reality it's not. And this is a vary with the temperature, and it's a very strange behavior for water is that it has a minimum scattering at temperature about 24 degrees, and those dot or circle are the observation, and this orange or yellow line are the previous model. You can see they completely get this temperature dependence wrong, where this blue line is our model, which can capture this temperature variation very well. And recently, we just, this paper is under review. We want to look at this pressure, how this seawater scattering changes with pressure. This has never been done before, and we are looking. The reason we do this is because Argo, particularly biogeochemical Argo, now they take measurement all the way down to 2,000 meters. And at the 2,000 meter pressure is about 200 atmospheric pressure. So at that high pressure, how much light scattering is due to water. So that is really promote us to study this. And what we found out is that at the pressure increase, if you look at this curve, at the pressure increase, scattering decreased by seawater, just by seawater. Scattering decreased by seawater. At the 10,000 meter, the decrease about 15% decrease relative to the surface. Now this figure was shows this is the temperature salinity profile down to 3,000 meters. This is the real profile. The blue salinity and the red temperature. And we just took recently last year in Pacific Ocean, North Pacific Ocean. And if you look at this blue curve, ignore the other one, look at this yellow curve. What the yellow curve is, we put the temperature, put the salinity into this seawater scattering model, our model, and we ignore pressure because right now the model doesn't account for pressure. This is what the seawater scattering looks like. This is the yellow line. If we put the pressure effect into there, you see this purple line actually is, instead of increase, actually it's a decrease. So this is what our recent work. We hope for the papers under review, and we hope we can, once it's review accept, we can release this to the public so people can use to correct for their seawater scattering. So now we have measurement, and we have model, we can simulate scattering by water pretty well, and we can study scattering by particle. To study particle is very easy. If you look at this, the blue line is the total. We take a measurement, is the total scattering, and this the red line is we calculate the scattering due to seawater, and we subtract this. We subtract this, and this yellow line is what the scattering that only attributable to particles. Now we have scattering that only due to particles. Now we have this measurement, now scattering by particles. What we can do, how can we use it? So the thing actually conceptually is very simple. What we do, we build a library. Or we can see, we build a library, and if it's an elephant, this is how the scattering looks like. If it's a zebra, this is how the scattering looks like. If it's a bird, this is how scattering looks like. This is a basic concept. If we build a library, we go out to measure to find which one match, then we know what the animal is or what the particle is. So how do we build this library? And we do the library, this mostly in simulation. So we need, remember at the beginning, I see it varies with the composition, size, shape, and structure. So we have to account for all those to build library. To build this library, we just look at literature. We look at literature, what's the typical for oceanic particles, what's their refractive index. We know there are bubbles, and the bubble reflecting the points. Those are relative to water, okay, relative to water. Bubbles, and we have the organic matter typical refractive index 1.02 to 1.1. And for mineral particle, inorganic particle, they're reflecting at 1.1 to 1.22. This is typical range. So we know this composition within this range. The size of particle, and many of you study fish, and when we study this light scattering, typically we ignore fish. The reason we ignore the fish is not that they are not important, it's because the number of fish is relative to the small particle too fewer. So their contribution, they do contribute, but their contribution too small. So typically ignore the fish. Of course, we can find the extreme case, like if you just look at light shoot a wheel, of course it will change, right? But in most cases, when we took measurement, we ignore fish. So those are all those particles. Doesn't necessarily mean they're dead. Phytoplankton, we have to account for phytoplankton. And the size distribution, and pretty much all the oceanic particles, their size distribution is log normal distributed. And what about the shape? And this is the one challenging thing. All we know, there are no spherical particles in the ocean, right? Except bubbles. Bubbles sometimes spherical, or oil droplets sometimes spherical, but there's no spherical. But the thing is, they are not spherical. It's not a shape. The simply tell what it is not. But so for us to simulate, we have to make an assumption. So what assumption we made is we assume they are represented by this six-sided hexahedra shape. Then you may why you pick this shape, and their study showed this using this shape, they can simulate aerosol to the little particle in the air pretty well. So we use this shape to represent the general shape. And for bubbles, we pick it out. We just use this sphere, but with the coating to represent the bubbles. Now you ask, how about the structure? Exactly what we are doing now is we assume those particles are homogeneous. This is one limitation. We are improving again, there are no homogeneous particles. If you look at the phytoplankton, certainly they have cellular structure, not homogeneous. So, but now we assume homogeneous. So with this, and then we build this library, and so far, and we build about 200 those different particle species, and each one represents one line here. So you can imagine this one line represents a different animal in the zoo of the ocean, or we call the particles, different particle species or population. Like then you may ask, what is one particle? Let's see, one diatom, one species diatom. That's one we call one particle population. They are quite unique. They have their size. So this one diatom species might represent by one of those curves here. And we built about 200, from very small particle to relatively large particles, about 200. Now with this library, and now we just do our work. In this, if you look at this, this gray line. The gray line is what we measured volume scanning function. And we have model, and from this we can see, oh, there are those different particles that exist. Because when we put them all back together, we can completely reconstruct this observed angular scanning, which is represented by dashed line. Okay, those are all different individual, different particles. And here we simply tell what the particle is, represented by refract index and their size distribution. And this B is their concentration, relatively speaking concentration. On this figure, it shows their size distribution. If you look at this, all you get, oh, they are quite messy. This is a different size distribution. Yes, I totally agree. But this gives us everything to do the study I'm going to show you. And one thing we can do is do all the particle size distribution by each different particle species. One thing we can do, we add all of the particles together, right? We have this size distribution of diatom and size distribution of different phytoplankton. We add them all together. When we add them all together, what we got the total particle concentration at each side. This is called particle size distribution. So this black curve is when we add all the individual lines together, this is how it looks like. This is the particle size distribution, and this red line is the particle size distribution derived from list 100. This is the commercial instrument. It's frequently used to study sediment, and this is what the particle size distribution derived from this instrument. And this black line is the particle size distribution derived by our method. So you can see those two agree very well at this range. Then you may ask why this red line stops here. That's because of instrument limitation. It only measures at the forward angle. It stops at the 15 degree. It cannot see any particle smaller. Where our method, we measure the scattering at all the angles, including forward angle, backward angle, and we were able to get particle at even smaller size. If you look at those, they're quite small, the 10 nanometer or 0.01 micrometer, so they are very small. So now we can see we can get the particle size distribution very well. And this is one detailed study. We look at this Mobile Bay, and we measured in 2010 Mobile Bay. This is at individual station. You can see the agreement. Overall, the agreement is pretty well. The two observations agree about within 10%. And this is the most recently we did last August to September. We spent about 35 days in North Pacific Ocean. We have this sample station. This is what we got at this station. Particle size distribution obtained by different instrument. And you see the different color obtained by different instrument, and you see that all these instruments, they if you lay them together, they agree with each other pretty well. This at this station, and this one's at this station. We are still analyzing this, and this project is one funded by NASA Export. So now we see we can get this particle size distribution very well. So what else we can do? And I'm pretty sure many of you are in this oceanography. Sometimes we filter the sample, right? We filter the water. We collect water, we filter. And sometimes we use the filter pore size different. And here I simply use the pore size at 0.2 micron. The typical use, we separate the particle into suspended and to dissolve. So this gray vertical line is about the size 0.2. What I do, I pick all of the particles on the right-hand side of this 0.2 or bigger than this. We take it out, and then we group them together by their refractive index. Remember, this refractive index tells us what the type of particle is. They're organic, they're inorganic. So I group them together by their refractive index. This is what they look like. Okay, we group them. And I can further group them. Further group them is I group everything with refractive index less than 1.1. So those are size bigger than 0.2, refractive index smaller than 1.1, all the size greater than 0.2 micron, refractive index greater than 1.1. Smaller than 1.1 index is organic matter, typically called organic matter, and greater than that is inorganic matter. Now we can do this, we know their particle size distribution, then we can estimate their mass, what their mass concentration. And by doing this, we compare with this mass concentration derived from this loss on ignition. You know, their typical study, we can measure what the mass concentration of inorganic matter, mass concentration of organic by burning, furnace, heating. So we can do this in the lab, and we can also do this, use this light scattering. You can see the comparison is pretty good. And this particular we did in the Mobile Bay, and this inorganic matter, organic matter, they add those together, this total suspended sediment. So this is another thing we can do. We can do this simulate filtration and look at the different composition of particles. And we can do many other things. For example, this, we look at this, just look at the phytoplankton. By looking at this, we pick out what are the phytoplankton. Typically, phytoplankton in this optical modeling, their size greater than 0.2 micron, their index is from 1.02 and less than or equal to 1.1. And this 1.1 is represent diatom, the shell of the diatom. So if we pick those particles out, we estimate their chlorophyll concentration and compare to the HPLC determination. Again, you can see the agreement is pretty nice. And this we can do similar to this, but we just look at the different type of particles. Look at amorphous silica and clay mineral, and look at this and estimate their mass concentration and see agreement with the lab determination very well. So this is the other thing we can do. What else we can do? We can look at the bubbles, individual particles, look at the bubbles. And this is when we look at the bubbles using this method and compare to those determined by acoustic. And you can see the agreement. This is the red line. Sorry, this is the black line is acoustic, and this is the blue line is optics. So their agreement, particle size distribution very well. And we look at this one size, 9.5 micron, over the time, this evolution of particle, you see the two methods also agree very well. So now we did is look at those particles that there are some ways to measure, so we can validate. We can also look at those particles. So far, there are very little way to look at. One of those is dissolved particles. Dissolved particles, how much is scattered, this is still debatable. Many people in our field, when they look at the dissolved particle, yeah, they don't scatter light or they scatter very little. Actually, all particles scatter light, we just don't know. What we found out is those smaller particles, dissolved particles, actually they scatter light, particularly in the backward angle, quite high. There's a fractional contribution. They can contribute 30 to 80% the scattering in the backward. And also we find out that their backscattering correlates very well with absorption, Xiadong absorption, meaning those two are very similar, or they are the similar particle pool. So now we see this, by measuring this angular scattering contains a rich information of particles. And we have developed the technique or the methodology to utilize this. And this is a powerful biogeochemical tool. And personally, I think this is quite important, and very few people study this, but we feel it's very promising to study different particles in the ocean. My work over the past 10 years is mainly funded by NSF, NASA, USGS, and even some USDA grants. And also I collaborate with many people. I'm grateful to their generous support from those people. And I'm just myself. I can only do little, but without the help of my student postdoc, I cannot do all those things. So I thank them here. And finally, I thank you for inviting me here, and thank you.
So I know I have a question. So the problem that I've had, I work with coupled biological hydrodynamic models a lot. And I'm the biologist, and we use these models to estimate temperatures a lot. And it's very frequent that the temperature estimations are off by 1, 2, or 3 degrees, which doesn't sound like much for hydrodynamics, but it's a huge amount for biology. And the way the models work is in order to fix this, they change the water quality, which I assume is the ability of the water to absorb and release temperature at the surface. Does what you do advance that problem? Because this is a big problem for a biologist.
One thing this temperature estimation is wrong. It could be because what you call water quality. Those particles, they absorb light, they scatter light. And if the light absorbed, pretty much the most energy end up heating the water column. So it could be, I don't know, but certainly it could, the particle. And there are studies, the heating rate, because of the turbidity of the water quality.
I was just wondering, in the models that you're using to estimate the scattering properties, do you ever try and estimate the ability to retain and release heat as part of that?
No, I haven't done that. But it's not that difficult. Once we know the particle, we can estimate what their by mass base or volume base, what their heat capacity. If we know we know their concentration, heat percent, we can estimate how much heat they absorb and light propagate in the ocean.
Any other questions?
So you're measuring inherent optical properties. I'm wondering about the backscattering component. Can you decompose what you're doing into something that could be used for a remote sensing approach?
This is one of the purpose I try to do this. It's called the remote sensing, and I'm heavily involved in this ocean color. This purpose is look at. If you look at the remote sensing, and sunlight here goes to this, and we look at the different angles of this. Basically, sensor is look at this angular scattering. Its effect it is. So if I didn't show here, but we do develop a model, ocean color model, where accounting for this angle, different angle.
And that's specific to each sensor?
So to each sensor, how their path. And this is particularly important is in the geostationary satellite. The geostationary is looking here, as the sun goes up and down, you see sun coming here. The effect called the different angle of observation.
Any other questions? Well, thanks for coming over.
Thank you.